Hey, this is Dr. Riley, and in this module, I'm going to introduce the mole and show you some basic calculations using that unit. But first, we're going to imagine that you've been asked to cater an event with a huge cake. The recipe you have for the cake calls for 36 eggs, and you're not about to go to the store and count eggs one by one off the shelf until you get to 36. You're much more likely to go in and grab a few dozen, whatever number that is. So the conversion that you have between 1 dozen is 12 eggs is something that you're likely to know by heart because it speeds up your ability to convert between the two in your head whenever you need to. So to solve this problem, you begin by writing out that you have 36 eggs in the recipe. You'll notice in this calculation and all my other ones, I'm going to be very careful to include the units because it's my way of checking that I have aligned the calculation correctly. Now I need a conversion factor to get myself between eggs and dozen. This case we just stated there are 12 eggs in every dozen eggs. So 12 eggs in the denominator per dozen in the numerator allows me to cancel the unit eggs and leaves me with the final unit of a dozen. Multiplication here gives us that this requires 3 dozen eggs. Boy, it's a lot faster to count 3 dozen than it would be to count 36. At this point, you should be wondering why I'm talking about cakes. But chemists routinely need to count atoms and molecules, but they're too small to take off a shelf and count by hand. In fact, a handful of atoms would be an enormous number. So counting molecules by the dozen absolutely will not work. But it would be helpful to find a number that can be used to efficiently count entities such as molecules or atoms. This is where the mole comes in. Now the term mole is spelled the same way, M-O-L-E, as the adorable fuzzy creature depicted here or the spot on your face. But in chemistry, a mole is actually a standard base unit for the amount of a substance or entity. So just as 12 is to a dozen eggs in a bakery, 6.022 times 10 to the 23rd is to a mole of atoms or other entities being counted in chemistry. You should be asking where this large and slightly bizarre number came from. First of all, it's large because atoms are small, and we use many, many atoms in a single reaction. So we want to count a lot of them in one unit at a time. A mole is actually equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. But it can actually be used to count anything, even eggs. So this number is referred to as Avogadro's number here, so named for the scientist. Depicted it right. So just as a dozen eggs is 12 eggs, a mole of eggs is 6.022 times 10 to the 23rd eggs. Let's practice the concept right away. If a penny contains 2.4 times 10 to the 22 atoms of copper, how many moles of copper are in there? Well, let's convert between atoms of copper and moles. The first thing I want to begin with is placing my starting number in the numerator, and I need to include the units. So that many atoms of copper. Now I need a conversion factor. Regardless of what I'm trying to count, I'm going to use Avogadro's number to get myself to the mole. By definition, Avogadro's number is the equivalent of number of whatever I'm counting per mole. So I'm going to say 1, let's see, what's in the denominator? 6.022 times 10 to the 23rd atoms of copper in the denominator is 1 mole of copper atoms. This enables me to once again cancel my units and leaves me with the number of moles of copper, which is what we were looking for in the original question. When you perform the mathematical operations and check for significant figures, your final answer will be 0.040 moles of copper. One thing that's really nice about this type of calculation is that it's very quick and easy to go back and check that you entered it into your calculator correctly. So I've put our final answer, 0.040 moles of copper, back up in a numerator, and we're going to work our way backwards to see if we can calculate how many atoms of copper that is. So now we're starting from moles and working back to atoms. We still need Avogadro's number, but we're going to use it in a different way. So because we have moles in the numerator, we now need moles in the denominator. 1 mole of copper atoms. How many is that? It's 6.022 times 10 to the 23rd. Oh, sorry. When I multiply this out, I get my original answer. It's 2.4 times 10 to the 22nd atoms of copper, or copper atoms. They mean the same thing. So again, you can go back and check any one of these calculations very quickly by simply working backwards. Plus, it's good practice. Let's try working with a different metal. We'll look at iron for a moment. Let's calculate the mass of 1 mole of iron. Now, we haven't talked about the relationship between mass and a mole yet, but the mass of various substances varies. So, for example, if we were looking at a mole of eggs, ostrich eggs compared to chicken eggs, even though you'd have the same number of eggs, the mass of the chicken eggs will be less than the mass of the ostrich eggs because per egg, the ostrich egg weighs more. Same thing applies to atoms and molecules. You can actually quickly reference a periodic table to find the molar mass. This is actually the mass in grams of 1 mole of the substance. So for an atom, the mass is simply right below the chemical symbol, right there. That means that there are 55.845 grams per 1 mole of iron. This is an incredibly handy thing to learn. Now we can actually quickly convert between moles and mass. So if we start off to answer this question with 1 mole of iron, and we convert by saying, well, 1 mole of iron is 55.845 grams. We cancel. This is a pretty quick calculation, isn't it? 1 mole is 55.845 grams. Let's step up the calculation a little bit. Let's try to find out the mass of 2 moles of iron. So we're going to begin by writing that we have 2 moles of iron specifically, remembering that the mass of different entities is different per mole. We go to our periodic table and we find that 1 mole of iron is 55.845 grams. Cancel your units to make sure you're doing things correctly. When you multiply through, you'll find that this is 111.69 grams of iron in the 2 moles of iron. Now we want to flip the calculation around and start with the mass and convert that back to moles. So if we want to determine the number of moles of elemental iron in 36.5 grams of iron, we set up the calculation by writing out 36.5 grams. We note the conversion factor from grams to moles, and we'll multiply through. Again, our conversion factor is straight off the periodic table for an atom like this. So in its elemental form, iron is 55.845 grams of iron per mole. Again, we double check that our units are canceling. We multiply through, and in this case, our answer is 0.654 moles of iron. You'll notice that I make a habit of noting what I'm counting in every calculation. Grams of iron, moles of iron. It's because molar mass is specific to the thing that you're measuring, and it's a good habit to keep track of what you're measuring in these calculations. As they become increasingly complex, you'll rely on this more heavily. So at this point, you should be able to convert from number of atoms to moles, or vice versa, and the number of grams to moles, and vice versa. We'll explore multi-step molar conversions in a separate module.